So in the last lecture, I was talking about conditional probability. So suppose that fxy is the joint mass function of discrete random variables xy on a probability space. So recall y given x equal to x is the random variable defined as, okay, so with mass function. Okay, with mass function. So if we write y given x of y given x, this is what how we write it. So this is just the probability of capital Y equals small y, given that this. So the thing is, this x is fixed, but y is a variable here, okay? And this is probability of, so you can write like this, that so y equals, so x equals x, y equals y. So that is f of x comma y. Let me write here probability. This provided okay. So this is just recall conditional. I am just using conditional probability. Probability of A given B is probability of A intersection B. Probability of B. Of course, for this to be making sense, probability of B must be not equal to 0. So x is in the range of capital X. Okay, so this is the thing. And this is exactly equal to f of x comma y divided by probability of, okay, I can write like this, f of x, fx of x. Okay, and so where, since the given data is a joint mass function, you should know how to compute the marginals. Fx of x is the mass function of x, and so we have formula fx of x is equal to summation. So you will sum over all possible y, fx y of x comma y. Okay. So and we commented about this x e of y comma y given x, and that can be computed. This is equal to fx. Yeah. Okay, so the mass function, yeah, fy x of y given x. This is how it is written. Times probability of y equals y given that x equals x. What did I do? No. Times y. And you think of this, so the idea is, yeah, so think of expectation of y given x equals x as a function of x. This is what I was saying at the end of my last talk, as a function of x. Okay, so we get a new random variable, and denoted. So this is psi of x, okay, denoted psi of capital X. So you see, you think of psi of round bracket x as I told you, the composition omega to x. So this is already two real numbers. And you take psi, compose with psi, and you land here, real numbers. So this composition is indeed a random variable, and that is denoted like this. Yeah, and just to bring out the dependence of this, in fact, so this is a certain function of x, capital X, and therefore a random variable. And that random variable, psi of x, a more appropriate notation is just simply write y given x. Given x. Okay. So the important thing to remember is that expectation of y given capital X is a random variable. So this is very important to know. It's a random variable, not a number, not a real number. Okay. So once you have this clear in your mind, then it makes sense to talk about. Okay. Go to the next page.
Excuse me.
Yes.
Can you explain how it's a random variable?
Yeah. So this is an you can think of it this way. This is a notation for this random variable. It is the most meaningful notation, self-explanatory notation. I already told you this is a random variable, and it is denoted like this. Why is it denoted like this? What is the value of this random variable? Okay, this I should explain. So when I say this is a random variable, it's a random variable on what probability space? So I explained that in the next page. We keep this here in front of us. So on, so when I go near the margin, the round becomes more like a diamond. On omega, the random variable e of y given x which is equal to is defined as follows. Is defined as follows. I'm going to repeat myself. Defined as follows. So, so suppose you call this z, then you should find out what is its value on omega. So e y x on omega is equal to, okay. So think of psi x of omega, psi x omega, which is by definition psi of x of omega, okay. But psi of x of omega, you call it little x if you like. So this is same thing as expected. So now apply, and so this is a real number. The moment I write x round bracket omega, it's a real number. So this is like a little x. This is by definition expectation of y given that x is equal to x omega. And now I have a random variable. I mean, what is that random variable? This conditional random variable y given capital X is equal to little x, and it makes perfect sense to talk about expectation of that, which is a real number. Now this is a real number. You understand? So this is exactly the way this random variable e of expectation of y given x is to be understood. I hope it's clear. So you just apply.
Sir, sir, can you scroll up the page? It will
Yes, yes,
be
yes.
a
Sorry.
little above. I mean, I think I missed a part above this.
No problem. I'm in no hurry to rush through the syllabus. If I leave out some parts of it, so be it. I want you people to understand what I'm doing. Clear?
Yes, sir. I think it's clear now.
Uh, yeah, um, you may have to again go over it at your home and think about it. Think about it. Only way that will lead to understanding. Yeah. So um, it's a very important concept. You have two random variables x and y, and your joint distribution function is given. Then okay, so you get a new random variable. You get several random variables out of it, and this is one such. Okay, so um, the important thing to notice is that, so you are taking expectation of y, okay, but the variable here is x is equal to x, and that little x is being thought of as a variable. So that is the basic thing. I mean, you should keep that in mind. That's why e of x given y given x is written as psi of x. You should not think of it as psi of y. I mean, yeah. So this is something you should remember. Okay. I think things will become clear if we do an example. I'm going to do an example. But before that, I stated this theorem. What is the, yeah, so yeah, I think I stated that theorem somewhere here. Yeah. Hmm. Expectation of, so expectation of y given x, that is expectation of psi of x, this is equal to, this is definition anyway, there is no content in this. So this is equal to expectation of y. When you just simply write expectation of psi of x is equal to expectation of y, it sounds a little mysterious. That's because in the notation psi of x, y is suppressed, y plays a hidden role. So better to write like this. Now it's clear that whatever you have should depend on both x and y. The surprising thing is it depends only on y. And in fact, it is the expectation of y. So we prove this. Excuse me, somebody at the door. I just have, just 1 second, please. Okay, we just proved this. That's it. There's nothing to. Yeah. But this way of writing explains. So expectation of psi of x. So whatever it is some function of x, and the theorem of the subconscious.
Sir, unconscious.
Unconscious. I really cannot understand why it is called that. I would rather like to call it sleepy statistician. Anyway, that says that it is psi of x times probability of x equals x, which is this. Yes. Okay. This is equal to, but unpack this. What is this? This is a yeah, expectation of, by definition, expectation of y given x equals x, sorry, times fx of x. So the sum is here over x, and here also over x everywhere. This is equal to, now unpack this one, the definition of that. This is y times, yeah, f, I write one more step, okay, f y given x is equal to, okay, wait, the notation is just simply that, y given x of y given x, fx of x. And now substitute what that exactly is, x summation over y, y, and this one is, yeah, I think fxy, x comma y, pay attention, and divided by fx of x and times fx of x. So I scroll up and show you what we had. Yeah, you see, this is where, except that I have written also x comma y here, indicated it more properly. Okay, so that's what I had substituted. And now these two cancels. So summation xy and y fxy x comma y. But now change the order of summation. So this becomes summation over y, y is constant, summation over x, fxy, x comma y. But that's exactly the marginal summation over y, fy of little y. And by definition, this is the expectation of y. Okay. So if you, so this is it. That's all. There's nothing more to it. And
Sir,
yes,
how did you write expectation of psi x like in the source line?
you just write. So psi of x is by definition this. No, I'm just
Yeah, but,
applying the definition.
how is fx x there?
This fx, you mean?
Yeah.
But that is, this comes from, because it's a, expectation of g of x is equal to sum over x, gx of probability capital X equals small x. That's exactly fx of x.
Oh, okay, sir. Yeah.
Yeah, so this is the mass function of x.
Yes, sir. Got it. Thanks.
Yeah. So that's it. So here fy is a mass function of y. So by definition of expectation of y, it is sum over y times fy of y. That's it. So you have the answer. That's it. QED. Okay. I want to do an example. This example is given in the book, but it's a beautiful example and illustrates the concepts and so on. I like this example, which is the reason I want to discuss it. Okay. Let me take out that page. Yeah, so it's a nice example. Hmm. So I write here. A hen lays n eggs, capital N eggs. So where n is a random number which follows, I write only briefly, where n is equal to Poisson distribution with parameter lambda. In other words, the number of eggs that a hen lays follows Poisson distribution. Okay, yeah. So on some day it may lay 2 eggs, some days 3 eggs, some days no egg at all, and so on. So we don't know the number. That number, if you call it little n follows Poisson. Little n is a random number whose distribution is given by, whose mass function is given by this Poisson variable, parameter lambda. Each egg hatches with probability p. Probability p 0 less than p less than 1. Let's just assume that. And on a particular day it may hatch 5 eggs, and each one hatching is independent of the other. So I don't write that full thing because it takes a long time. So if you just write briefly independently of other eggs. Okay. Let k be the number of chickens. Number of chickens. Okay. Which is of course a random number, and so it's a so k, actually the right way to say that is that k is a random variable that counts the number of chickens, but written briefly like this. So find expectation of k given capital N, expectation of capital K, and expectation of n given capital K. All right. So okay, let us do this. Yeah, so which way is, let us okay, so solution. So the thing is remember that this is a random variable, this is a number, and this is a random variable again. Okay, so you have to find 2 random variables and 1 real number. Okay, so let us write psi of n is equal to E of k given capital N equals n. This is equal to, now this is something easy to find. You see, why so? Yeah, see, for any given, yeah, we can do it explicitly, or you can do it in, you see, yeah, each egg hatches with the probability p, okay, and it is all so it is independent of the, So an egg hatching is independent of other eggs hatching. Okay, so let me just do this. Sometimes it's better to do it. This is equal to,
Sir, why is the number of chickens a random variable, sir?
because first of all, given number of eggs that that the hen has laid, each one hatching is with probability p,
Yes, sir.
and
So,
how many of them will hatch, that will depend. It's not a fixed number, but it's you can only talk in terms of probabilities.
okay,
Okay,
sir. So,
and
so,
now,
so,
yeah,
uh,
number of eggs that it will lay, that
yeah,
also is a random number, random variable. So
yeah.
there are
Okay,
two random variables involved. So if you like a random number, if I
okay,
just
sir.
write here,
Okay, sir. Yeah.
random number of eggs, number of chickens. Okay. So you just apply the definition here, there's nothing much to say. This is equal to K times uh, yeah, probability of capital K equals K, given that n equals n. Okay. So this is a K, whatever. Okay. K can only go from 0 to n. And this follows a binomial distribution, no? So, it's like you have n coin tosses, each one turns head with probability p, and you are counting number of heads. So, this will be, you can further expand it. Let me write that. I think it's better to do it after one more step. So, K probability that capital K equals K. Go a little slow, but doesn't matter. So this I'm just writing the definition down. Probability of capital N equals N. So you see this comma means and. So this is the definition. No, we are just applying conditional probability. Okay. So this is equal to K times this. You see, you have fixed your N now. Okay, and that varies according to yeah, this n choose k, p power k, q power n minus k. Okay, and divided by probability that capital N equals n, and that is common for everybody, so I may as well put that here. Okay. Here. Yes, I seem to be getting something different. Oh, this n is fixed now. K equals k. Okay, so here probability.
So we don't have this.
So this there is going to be a cancellation. Actually, we may directly write this for a given number of n. This is a number of eggs. This is directly equal to this. We don't need to write it, but even if you write it, you have to just, because the number of each egg hatching is independent of the n, this will become, this k and n are independent random variables. That's what it means. So although what I wrote is not incorrect, so I could have just written probability that k equals k. All right. So there is it will get cancelled with this one. So I get this. This is equal to n times k, n times p. Yeah, this is just because it follows binomial distribution. So this is n times, so k equals 0 to k equals n, and that is just np. And now notice that, you see, you have, so psi of n is equal to np, and therefore psi of n, capital N, is equal to capital NP. This is a very crucial step. So I just put it in a box. You understand this? You see, whatever it is, it should be a function of n. What function of n is this? You see, whatever, so psi for, you understand? Or if you want to, you can directly check this also. What is NP? NP is a random variable. What is its value at n? Well, the value at n means capital N equals n. So this is p times n. Okay. So both left hand side and right hand side returns the same answer. And so psi of n is equal to np. This is a crucial thing, I mean, in order for you to proceed. And now you can compute the expectation of k given n. Okay. Therefore, expectation of psi of n, you can write like this. Yeah, psi of n, which is same thing as expectation of k given n. This is what was asked. One of the things that needed to be computed. Expectation of this. So now expectation of a of this random variable. Sorry, I missed out on one more e here. Write that properly. Expectation of, if you want, I write one more step, k given n. I don't know if this was asked. It doesn't matter. Okay, so it's not asked, we don't need it. But anyway, I started writing. Let me write this. Expectation of NP, capital N, small p. This is equal to p times expectation of n, which is equal to p times lambda. So you can compute this also, there's no problem. Okay, let's switch back to blue color. And now, what do we want to know? Next, expectation of k. Yes. Yeah. So we needed to compute expectation of k by, this is, I'm going to write this. This is equal to expectation of psi of n, no? This is expectation of it by the theorem of subconscious, unconscious statistician. Okay, so this is just now we computed it, p times lambda. Is that clear? Okay. The next one is that's probability of, no, expectation of n given k. Expectation of n given k. So first of all, we need to compute so we need to first compute the mass function. The mass function. Yeah, Fn. Okay. n given k. This is how it is written. Okay, so let us do this. So this is for, in order to compute this, you need to compute probability of, so let's just write that first step. So what is it? F of, you just write this explicitly what it means. N given k of n given k is f of k comma n of k equals k, so k comma n divided by f of whichever way have I written. Okay. So this is equal to probability of k equals k, n equals n divided by probability of k equals k. So this is equal to, so this is probability of, as we did before, k equals k given that n equals n times probability of n equals n. Okay, so divided by probability of k equals k, but that you can use Bayes theorem, or essentially we are using Bayes theorem. This is again probability of, so this is a specific n, okay, but here it will be a variable k equals k given that n equals m times probability of n equals m. Now we know everything. So for a given n, k follows binomial distribution. So we just write that and choose k, p power k, q power n minus k times this one. This follows Poisson. So e power minus lambda, lambda power n by n factorial. Okay. So divided by n factorial. Whole thing divided by the sum. And of course, number of eggs hatching cannot be more than the number of this one. So here the sum is over m, mind you. Okay, sum is over m. And so here m has to take values bigger than or equal to k, and here probability of, so this is easy to write again, m choose k, k, p power k, lambda power, so q power n minus k, so m minus k times, what do I have? So this is lambda power m by m factorial e power minus lambda. Okay, sum is over m. You can simplify this slightly. Okay, I do some simplification. So this n factorial and n factorial will disappear, leaving k factorial here. And in the denominator also, we are going to get a k factorial in the denominator. So 1 by k factorial, 1 by k factorial will get cancelled. Leaving here n minus k factorial, that there is no way of getting rid of that. So n minus k factorial. And here, you see, in the numerator I have p power k, q power n minus k, e power minus lambda, lambda power n. And now write the denominator. So here, so This we got rid of. Okay. So what do I have? There's an m minus k m factor. Yeah, m minus k factorial in the somewhere. First of all, m minus k factorial is there in the denominator. M factorial had disappeared because there was an m factorial in here coming from this one, and p power k, that is a constant with respect to this. Q power m minus k, we just keep it m minus k, and lambda power m, I write maybe lambda power k here. I think it is better to write like that. Lambda power k, and here write lambda power m minus k, and then e power minus lambda. So maybe that e power minus lambda will get cancelled with this e power minus lambda. So at the moment write e power lambda. And since here k is bigger than or equal to m, we can simplify this quite a bit. So 1 by n minus k factorial. I don't know if I should do the entire simplification. Next step, so p power k cancels. Q power n minus k is very much present. Q power n minus k. E power lambda, e power minus lambda goes away. So I have lambda power n. So n minus k again. E power lambda. So this goes to the numerator. And divided by, what do I have here? Yeah, e power. So this one is exponential series, yeah. So e power minus, no, e power plus q lambda. Q lambda. Okay. And I think that is what I have here. So let me, one more step, we can write it better. So this you take along, yeah, q, simplify this slightly. Lambda q power q lambda power n minus k by n minus k factorial. Then e power minus q lambda. Okay.
Sir, I think it's m greater than or equal to k in the summation in the above thing which you wrote. No, sir,
In
down,
second,
down.
second formula.
This one here, there is no sum. See, n is fixed. I have fixed n here, no? See, I am just looking at only f and k here. I'm not computing the expectation. That will come later.
No, it's just a typographical error, sir.
Where?
Down, down.
Down for the down. Here.
Yeah, yeah. A little down. Over there, you wrote k greater than or equal to m.
Wait a second. So here, this is up to m. Okay. No, but here, no. Here in this sum, what do I have? Fk, no, P of k equals k. This, forget about the numerator now. In the denominator, I'm summing over all possible m. But the only time probability of capital K equals k, what did I do? So here, yeah, m has to be bigger than or equal to k, otherwise this is 0. So it is m, it's not n here, m.
Yes, sir, it is m, but in
Oh,
the
okay. Here. Oh, sorry. Okay. Absolutely, you're right. I mean, this is just, yeah, sure. I understood what you are. Of course. Yeah. Is that clear? Yeah. Okay. So now, so what was the thing? Yeah. So you see, our aim is to understand this E of k, E of n given k. all right? E of n given k. So you must think of it. What is the thing? Yeah. So let's just do this. Okay. Expectation of. Now we want to compute, having done all these things, expectation of n k equals k is equal to, we haven't done this yet, so we only computed the mass function. So n times f of n given k. Sorry, this is slightly, I care about it because later when you read it, you will not understand. Of n given k, which is what we just now found out. This is equal to, let us plug in the value and see what we get. Of course, summation is n bigger than or equal to 0, n times lambda q whole power n minus k by n minus k factorial e power minus q lambda. And turns out this is equal to, I write here what it is, k plus, so this n minus n, you write it as n minus k plus k, all right? And that plus k, so I skip a, okay, let me write this. Summation n minus k lambda q power n minus k e power lambda q divided by n minus k factorial. Is this clear? Why it is so? Because this n, I write it as n minus k plus k. And when it is plus k, I pull it out. Of course, I have the whole sum also. But that whole sum is just equal to 1. Okay, so that's why this became k. And now I have this. But this you readily recognize is the expectation for the Poisson with variable lambda q. So k plus lambda q. Okay. And now you must think of this. So you see, this is the variable here. So think of k is the variable. Therefore, we can write expectation of n given k. So this as a random variable is the same thing as the random variable k, and lambda and q are constants anyway. So it is just constant plus this. This is a very crucial thing to note. You see, you have, what are you looking for? You are interested to compute expectation of n given k as a random variable. But you write here expectation, so for a specific value of k, see whatever the random variable is, you evaluated it as at k. And so it's no wonder you will get a function of k. That function of k, you must be able to express it in terms of capital K. Some function of capital K evaluated at little k. Well, I mean, now in this case, it's obvious. You look at this as a function, evaluate it at little k, you will get capital K plus lambda q. If you had k square here, you would have had capital K square here. Okay? Is that clear? So this is the crucial thing. From here to here, it's a very simple thing, but important, because when you see it here, you just see only a bunch of numbers. But when you write it here like this, you have a certain random variable. Okay? And that's all that we needed to do. We have computed everything that was asked in that example. Find E of k given n. This is simplest one, and then this. So we did everything now. Okay. All right. Yeah. I have about 15-20 minutes. I want to work out some problems involving joint distribution function, So let us do this example. So if you have any question, I will answer that. Of course, we will do some more problems involving these expectations of this y given x type of random variable, expectations of conditional random variables. So that of course we will do, but I want to work out a few more problems in joint involving joint distributions and joint mass functions. Okay. So if you have no more questions, I will proceed further. If you have any question, I will answer that. So anyway, first I want to give this as a homework example, exercise. Rather simple exercise, but I want you to do this. If here x square or let me say it this way, we have x equals 0, where x random variable. Okay, discrete random variable. We are working with only discrete random variable. I can hardly wait to start on continuous random variables, but that will have to wait for some more time. Random variable which assumes non-negative values. What can you say about x? Okay, fine. So given that, so example or exercise, whatever, I want to work it out for you. X comma y have joint mass function fxy is equal to c by x plus y minus 1, x plus y plus 1, where x, y takes values from x and y. Take values in positive integers okay, integers okay. Find c and expectation. So okay, so find the c and this marginals fx of x, fy of y, and expectations. Okay. So first let us find this is a question, so solution. So, so let us just compute what is the fx of x. Fx of x is equal to, well, you just have to sum a given thing. So c being a constant, it comes out 1 by x plus y times x minus x plus y minus 1. Sorry, I wrote there. Doesn't matter. X plus y plus 1. Okay, and sum is over y. Y going from 1 to infinity. Yeah. This is equal to, so I have to write this carefully. So x is fixed and y is a thing that is varying. So c times summation 1 by x plus y. Now this one, you write it as partial fraction and you see that you get x plus, so something by x plus y minus 1 and difference x plus y plus 1, and when you do this you get 1 and 1, I suppose. Yeah, this will be okay because you get 2 and then there is a divided by 2, 1 by 2, so that 2 I take it outside. Okay, so this is equal to c by 2 summation 1 by x plus y times x plus y minus 1 minus 1 by x plus y times x plus y plus 1 and y going from 1 to infinity. Now you see there is going to be telescopic cancellation because it's like, whatever happens to this happens here but with a shift. Okay, so only the term y equals 1 will survive. Other terms are all 0. So this is c by 2. Other terms will just get cancelled. Of course, y, yeah, I don't need to explain anymore. So this is equal to y equals 1 term, I think. Yeah, x plus 1 times x, so or x times x plus 1. This is it. Okay. And now to compute, so this is your fx of x. So there is symmetry in x and y. So fy of y will have similar expression. Let us compute c. And in order to compute c, okay, to compute c, you use the fact that fx x is a density function, x times x plus 1, x taking values in integers, positive integers, is a density function, density. Sorry, I should not call it density, I should call it mass function. So mass function. So if you sum over this, it should give you a 1. Therefore, 1 is equal to c by 2, here c by 2. C by 2 times summation x going from 1 to infinity 1 by x times x plus 1. So this is equal to c by 2 summation. Now this also again can be expressed in a difference of two things. So write the small one first, or rather one with smaller denominator first. And then this will give us 1 by this, I suppose. Okay. And this is equal to so the first term alone will serve, first term survives, right? And only this one will survive. So this is equal to 1. So this implies c equals 2. Should be okay. That's it. Yeah, check these calculations. Yeah, I think that's all. So now you can try and compute the remaining parts. Do the calculation. Expectation and variance. Actually, it's very trivial. Okay. I want to discuss, I have time for one more problem at least. There are many more problems given in the book. I'm not going to, it's not possible as such. I'm running sort of behind the timetable. So, but please try as many problems as you can. And if you have some doubts, get your doubts cleared in the tutorial sessions. I keep repeating this several times. So suppose that x and y are random variables with mean 0 and variance 1. Okay. Also, expectation of x square is equal to 1. Expectation of y square is equal to 1. And so the covariance is which is equal to rho. That is, so recall covariance of this is e of xy minus e of x, e of y. If you recall, if x and y are independent discrete random variables, then exy would be equal to exey. That's also true for continuous random variable. We'll see that later. So covariance, yeah, is given to you to be rho. Then show that expectation of maximum of x square and y square. You have an estimate for that. You cannot exactly compute it, but there is an estimate. 1 plus square root of 1 minus rho square. Okay. Yeah. So in order to do this, you need to understand this thing, maximum of squares of two random variables. Okay, so when you are interested to compute this, so this will naturally involve computing. So let me write that expectation of x square, maximum of x square maximum of x square and y square. So, okay. So, okay, you need to compute this. In order to do this, you need to understand how to express maximum of two numbers, a and b. And let us say a and b are both non-negative. Anyway, this will work. Maximum of a and b is a plus b by 2 plus absolute value of a minus b by 2. Let us do this very quickly. Is it clear? I suppose. Okay. Suppose b is bigger, then this will be b minus a by 2. So you will pick up b by 2, and then a by 2 minus a by 2, that will get cancelled. So, and if a is bigger, you will pick up a by 2. So both return a and both return the same value. Therefore, this is a thing. And now, so you see, you can use this expectation of maximum of x square and y square is equal to expectation of, I'll have to be quick, expectation of x square plus y square by 2 and then plus expectation of x square. So absolute value of, now you have to write absolute value of x square minus y square by 2. Okay. So this is a very simple 1 by 2 expectation of x square plus expectation of y square, and you are told that that's equal to each of which is 1. So this is 1 by 2 times 2. Okay, that's good. Plus expectation of this. So this 1 by 2 can be again pulled out. Now expectation of absolute value of x square minus y square. Okay, and now you think about that a bit. So expectation of, expectation of x square, absolute value of x square minus y square, you write it in this fashion, is equal to expectation of, this is square root of, okay, square root of x square minus y square whole square. So this is a trick. Is equal to expectation of square root of, so this can be factored. So x minus y square times, yeah, so x plus y. So this I can just ignore this. Yes. So it is basically square, okay, square root of x minus y square. That I will have to write. No, okay, let us just write this. Maybe still not ready to get rid of this. Okay, so what does this become? Okay, fine. So this is what we do. Okay, so maybe this is not so helpful. Okay, so we need to use this inequality, expectation of xy. Let me write that. Which way does it go? So you see, the thing is here, the rho, yeah, E of xy, this is bigger than or equal to. So we are going to use this. Let me write this. UV is bigger than or equal to expectation of U. That's what I want. Yeah, this is okay. That's right. I'm writing it correctly. 2 times. Let me just check. I forgot what is the thing. So we okay. So you have xy. So this is just coming from Cauchy-Schwarz inequality, which is what I was trying to write. So where is this? Seem to have. Okay. Now I should get back to. Are you able to see the board? Yes.
Yes, sir.
Yeah. So it's the other way around. We will see. This is. Okay, I think this is true. So this is called Cauchy-Schwarz. It's easy to prove it. I just don't remember Cauchy-Schwarz inequality. And this also is an exercise. Once you have this, so you need to consider, yeah, this is where it becomes important. Suppose that,
Sir, the square is inside the brackets, right?
yeah, I suppose so. Yeah, I suppose so. I just didn't check properly. 1 minute. Square is inside the bracket, absolutely, but for one of them only. So here is this. I should have been more careful. Here it is square inside the bracket. This is what you need to use. Okay. Yeah. Once you use this, so you write here. You see, basically this x minus y square. I'm already out of time. This is x square plus y square minus 2xy. So sorry, there is a square here. Square minus 2xy. That's right. Okay, so if you use, that's right. So you use this inequality. Okay. So here you see, that's what you want. You want to replace this. So you see this product of two quantities under square root. So whatever is under square root, you think of that as u and v. And u square will then become, v is just x minus y square. So you apply this for, so let me say at least, because I'm out of time, take u is equal to absolute value of x minus y, and v is equal to x plus y. Anyway, xn, so you can also put that in parenthesis bracket, no problem. Absolute value, doesn't matter. So you just do this, okay, and then apply this, then you know that this is less than or equal to expectation of u square, which is exactly x minus y square, times expectation of x plus y square. This is exactly what I wanted. Holds that square is within the expectation. So now I have to compute expectation of this, which is expectation of this. Now this is equal to, you are given something about this. This is 2 minus 2 times expectation of xy, which is rho. So this is this, and yeah, so similarly E of x plus y whole square, this is equal to 2 plus 2 rho, and these, so therefore I must take the product, and there's also a square root here outside. I should not forget, because this quantity here, it is square is outside. Therefore, this quantity becomes, so I write here, this quantity, after you substitute it, becomes equal to under square root 4 times 1 minus rho square. But there's a half outside, and that half, and there is a 4 within square root, that will simplify to give you the required inequality. Sorry, I'm completely out of time. So check this, that's all. So you have to use this Cauchy-Schwarz inequality. Proof of Cauchy-Schwarz inequality is already given in the book, but you go over it and understand it. Okay, that's all for today. So let me stop sharing.
So does the expectation forms any metric over the random variable space, or some? Does the random variable space contains the metric, contains expectation as the metric? Then we can directly prove Cauchy-Schwarz from the Cauchy-Schwarz
So
in linear algebra.
See, you require one important thing, which is what, see, so you need to, this is where that exercise becomes important. What does it mean to say expectation of x square equal to 0? So essentially, you are bound, you may assume that expectation of x square, and it's a very simple matter. You just have to compute the expectation of, let me say, what is involved in showing this Cauchy-Schwarz. It follows from the usual Cauchy-Schwarz, where you just have to understand only one thing. Suppose that the random variable only assumes non-negative values, then expectation is positive. Okay, that's the only thing you need to know. Nothing more is required. Then you compute the expectation of ax plus by or minus by, doesn't really matter, whole square. Now this random variable, whatever it is, it assumes non-negative values, right? And so this is greater than or equal to 0. You expand it, and it is greater than or equal to 0 for any value of a and b. and think of it this way, and that will mean that so discriminant is some, this is going to be some quadratic in a expression in A and B. Then you want to say the discriminant is positive or non-negative, and that's exactly what gives you the answer. Yeah, discriminant is less than or equal to 0. Yeah, I should say, because this is greater than or equal to 0. Okay, so that's all that is involved. So the relevant fact is, if a random variable assumes only non-negative values, then expectation is greater than or equal to 0. I hope that answers your question.
Okay, sir. Now, my question was a bit like, will it also form a metric on some space, on some linear space?
Oh, whether it will form a metric
The expectation.
expectation. Okay.
Yes. Then I was
Maybe
using
not.
the-
I mean,
Acha.
I don't think so. I don't think so. No, I don't believe that is true.
Okay. Okay.
Yeah. Okay. Yeah. Bye.